So this is the second video that's dealing with the content for this unit. The first one dealt with just kind of the basics of heat. This one is dealing with the methods of heat transfer. And we have three: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact. Okay. So if you are touching something, so like if you touch an ice cube, the ice cube feels very cold to your touch. There is conduction going on between the ice cube and your hand. Okay. So we're talking about direct contact. That's conduction. Convection, which is essentially a type of conduction, but there's a little bit more going on. So conduction here, this happens between, generally speaking, solid objects. If we're talking about conduction, we're generally talking about two solid objects that are in contact. With convection, this is the transfer of heat through buoyant mixing. So usually you're talking about a fluid. You've got some kind of fluid involved. It might be a fluid mixing with other fluids, or it might be a fluid that's working in contact with a solid. So a good example of convection would be like a radiator in a room. So the radiator is located near the floor, and it gets very hot, and it's going to heat the air around it. And what's going to happen? Well, that heat's going to expand and it's going to rise because it's less dense than the air around it. So it rises, and then cool air comes in to take its place. And so this is what I mean by convection. It's kind of like conduction, because the air is in contact with the radiator. But what's happening is it's not always the same air. You get what are called convection currents. So that leads to essentially more efficient heating as a result. Conduction, it's always the same two surfaces. Generally speaking, it's the same two surfaces in contact. And so that tends to be not as efficient with regards to heat transfer. But convection is a much more efficient method of transferring heat. And then the last one is radiation. This is the transfer of heat through electromagnetic waves. We commonly just say EM waves. There are lots of examples of EM waves: light, ultraviolet, infrared, radio waves, microwaves, gamma rays, X-rays. These are all examples of electromagnetic waves. And basically everything is radiating. You are radiating right now. You are radiating heavily in infrared. And in fact, most animals of a suitable size are radiating heavily in infrared. In fact, as far as I know, it's all animals. Maybe there's a few exceptions that I'm unaware of, but they all emit heavily in infrared. The sun, of course, is heating Earth via radiation. There's light coming from the sun, and that's what warms Earth. So there are lots of examples of radiation. These are just a couple. But objects can absorb the light, and of course, they will emit it as well. So these are the three methods of heat transfer. And the formulas that you see here, if you look at these formulas, you'll see it's all in terms of P. What is P? All right, P is power. We've already talked about power. It's the rate at which energy is transferred or transformed. In this case, it's the rate at which heat is leaving or entering an object. This is more commonly referred to as the heat flow rate, but it is, in essence, just the power. That's what it is fundamentally. So it's going to be positive if heat is entering the object. It's going to be negative if heat is leaving the object. And we talked about this already, but the unit for power is watts. That's joules per second. So if you go down to conduction, now this conduction, we talked about is heat through direct contact, but this formula is talking about the heat flow rate through an object. So let me give you an example. Let me do a simple diagram here. Might have an object, just a simple, perhaps cylindrical rod. Okay. And when we're talking about the heat flowing through, this is the rate that heat is flowing through the object. Because of course the rod is in contact with itself, and so heat is going to flow through it. So in this case, K is just a constant. It's called thermal conductivity. A is the surface area. Okay, what is the surface area? And specifically, it's the cross-sectional area. I said surface area, but cross-sectional area is a better term there. It's the cross-sectional area. So that would be this area right here. Because the heat, and I didn't indicate this, but the heat, say, is flowing this way. Okay, so if the heat is flowing this way, so there's the flow, it's going to the right of my diagram. So the cross-sectional area is this right here. L this would be L, that length right there. So this is A on the end. I'll put an A there, that's the area. This is L. It's the length of the object that is parallel to the heat flow. So the heat flow is going, you know, in my diagram, it's going horizontal, so that's how I know that's L. And then T1 and T2, these are the temperatures at the two ends of the object, whatever those temperatures are. And you can see here we're doing absolute values because in this case, we're just talking about the heat flowing through the rod. So in a general sense, to talk about positive and negative, there's no good way to talk about positive and negative in this kind of case, in a general sense. In some specific problem, you might be able to, you might define positive or negative being one way or the other, but we're not going to do that here because that would actually just lead to confusion. So that's why you see the absolute value signs. For convection, so this formula calculates the heat flow rate of a surface area that's exposed to a fluid undergoing convection. So you might have, for example, just some kind of plate, like so. I might have this plate, and there might be some air up above the plate. So let me just kind of color the plate in. So here's my plate, and we'll say that there's all sorts of air molecules or something here all above it. Okay. And these all might be going, you know, the wind, this might be wind, so the wind might be blowing to the right in my diagram. Okay, so H is the convection coefficient here. A is the surface area. So this here, this area, let me see if I can. Let me see if I can label this. This is my area down here. There we go. Okay. So this is the area that's exposed, in this example, to the wind. Okay. T fluid, that'd be the temperature of the fluid, in this case, the wind. So or the air, I should say. What's the temperature of the air? TA is the temperature of the surface area. And what we're figuring out here is the heat flow rate of this surface area. So is it gaining heat? So in other words, is it going to end up warming up, or is it losing heat? Is it going to end up cooling down? This, as you can imagine, is something that's very important for, say, houses. Or even if you're talking about people that are out in cold conditions. You know, the wind's blowing by. They talk about, in the weather, they'll talk about what does it feel like. So they'll say what the temperature of the air is, but then they'll say, what does it feel like? And that depends a lot on various things, including the wind. And so they kind of take this into account in those situations. The last one here, radiation. So there's three formulas here. The first one is the rate at which an object emits. The rate at which an object emits EM wave energy. Okay. So it depends on A. This is the surface area. So if you were talking about a person, it would be the area of your skin. E is the emissivity. This is a number between 0 and 1. If it's a perfect reflector, that means it reflects, it only reflects, it doesn't emit anything itself, okay? Then E would be 0. If it absorbs everything that comes in, then it would be a perfect emitter, and E is 1. This is another example. We talked about the coefficient of static and kinetic friction. Those coefficients were unitless. This is another value that is unitless, the emissivity. Sigma is the Stefan-Boltzmann constant. There's the value there. And T, this is the object's temperature in Kelvin, of course. And this is going to tell you, see the minus sign because the object is losing. Because it's losing, so this is the power for the object because it's emitting this, so it's losing all this energy. Now, it's also absorbing. So this is the formula for when it's absorbing. Notice there's no minus sign, and the other difference is it says T sub S. That's the surrounding temperature in Kelvin. And so if you want to figure out the net, the net heat flow due to radiation, you just have to add those two together. That's the idea.